Okay, so I asked the question, what are the significance and contextually, like what does this number mean for this function we came up with? And so let's look at that. Like first of all, let's actually start with this number right here. So we said that cosine x, by the way, this is a cosine function. A cosine is a trigonometric function, and something about all trigonometric functions is that they are periodic. What periodic means basically is that this function repeats itself over and over again at a regular interval. So the distance between this point here and this point here, and the distance between this point here and this point here is a constant. It's the same. It just keeps repeating. That's what periodic means. You can think of in nature, right? A natural occurrence of a period or something that's periodic is the seasons. So like winter, spring, summer, fall, it keeps repeating itself over and over and over again. And in fact, that's kind of why we have, it's very related to why we have this kind of shape when we have now graphed all the amount of hours and minutes of daylight every day of the year. So this number here, if we recall going back to basic functions, if we multiplied, so if we had f of x and we multiply it by a number less than 1, like 0.5, it stretches it out. If I multiply by a number significantly less than 1, so like 0.1, it really stretches it out. And so what we would expect then by multiplying this number here by a number less than -1 is that we stretch it out. So yeah, if we actually type that same number in, 0.0167639, it took that original cosine function and it stretched it out horizontally, kind of like a spring. Now notice also though, where we have, and you can see this kind of matches up, right? Where these are about the same location, right? This minimum and this maximum, and this minimum and this maximum are kind of the same location. So if I wanted to, instead of these being maximums, if I wanted them to be minimums, how would I make those big positive values be big negative values? I would just multiply everything by -1, right? So if I type in -1 right here, it makes now those minimums minimum. And you can see already, just by doing that this green graph we have down here is pretty close to this purple graph we have down here. I'm just going to change the color of this to make it a little more apparent what's going on. Okay, so the orange looks pretty similar to the green and blue here. All right, now let's say we want to move this data up, okay? So, well, actually first, what did we do? When we did this in the context of this problem, right, we have, our data represents all 365 days of the year. So the distance between a minimum point and a minimum point should be 365 days, because the amount of hours and minutes of daylight on this day should have been the number of hours and minutes of daylight on this day, same as this day. And so what we did was we took whatever the default period of this cosine function was. Period is the amount of time it takes to start repeating itself. Whatever the default period is, and we'll learn about that later, we made it much larger. We stretched it out and we made it to be 365 days. So this is like a modifier of some kind that made our original period be now 365. Okay, so what does this part do? Well, if I were to just type in that graph, like what is y equals 12.119? That's just a horizontal line, right? And it's a horizontal line that looks to be right in the middle of all this data. In fact, it's an average. It is the average amount of hours and minutes of daylight on a given day throughout an entire year in the location that we selected here. And so if we were to just add that up to this one, it's going to be a vertical shift. Okay, it's going to shift the data up. Everything, all the y values are going to be shifted up 12.1189, like units. And in this case, these are hours, right? Now, what does, now notice, like, the only thing we're missing here, we're missing a couple things. The numbers we didn't consider are this one here and this one here. And this one here. So this one here, we know that if we multiply a function, all the outputs of a function, all the y values, by a number greater than 1, it's going to produce a vertical stretch. So that's what that's going to do. Okay, so 2.08871. So we were at, actually, if we go back and look at that one a little more carefully, right? At this point right here, this data was 13.119, and then down here it was 11.119. So from here to here, vertically, right now, it's 2. Okay, and so if I multiply that, I put that data back in, right, 2.08871, then now if I look at the difference between this maximum right there and this maximum right here, now it's two times whatever this is. It's 4 point 0.16 or 1.7, whatever. Okay, and what that's corresponding to for this data is basically the variance, right, between the average is the difference between the average amount of daylight a day to like the maximum and to the minimum. It's the difference. So this value, actually, what we call it when we talk about trigonometric functions, it's called an amplitude. It's like an amplitude of a wave. You can think of it like that. And so the last number we haven't talked about yet is this 14.612, and this is pretty tricky. Now, if we put this 14.612, if we added 14.612 here to this x value, we'd be shifting the data to the left. We'd be shifting it to the left 14.612 units, so 14.612, and that puts our graph right on top of the other graph we had. Well, what does that mean? What is that doing here? Well, in the context of this problem, what this is saying, what this low point in this graph is saying, is that this is the minimum amount of daylight in a year at this location. Like 10.03 hours, which corresponded to, what did it correspond to? It was 10 hours and 3 minutes, or 10 hours and 2 minutes of daylight in a year. That's the low point right there. Well, when we think about a year, like just in our, just backing up a bit, what is the shortest day of the year? What is the day of the year with the least amount of daylight? That's called the winter solstice. So what this graph is saying is that 14.612 days before the end of the year, the start of the year, this is January 1st right here, right? If we go back that many days, that would be the winter solstice. And we're off a little bit. The winter solstice usually happens, I think, on December 21st. So we're off by about 3 or 4 days. But this isn't a perfect graph. Obviously, this orange line doesn't perfectly match the green data, and the green data itself isn't like a super duper accurate. But that's really important. All this information would be useful. Like, who would it be useful to? Anybody who is interested in using like solar panels in this place. Like, how much daylight do they expect per year? Anybody who wants to know about what kind of plants might grow best in this kind of environment. And we can also make these same things by looking at these numbers and how they match up to different functions. We can also make other important observations. Going back to the original example here, here was the graph that this came up with. So 1 plus r, where r was 0.199. Well, if we said that our data was perfect, like if we said that this black line matched the data perfectly, what this would tell us is that, because I have the 1 plus this r is what's called a percentage growth rate, essentially, for an exponential function. That means that this virus is growing by 19.9%, or basically 20% every day. So we would take a number like 1, right? And if we multiplied 1 by 1.2, we have this. If we multiplied 118 by 1.2, we would have this. And if it was perfect, then that would be the case. And then what does this S mean? Well, this S means something about, in the context of the rest of the graph, like how do we, like this has to do with the rest of the context. In this case, it's just a shift back. It's like extrapolating this data back to 0, basically. And so it's really interesting, the kind of information we can get off of a function.